All right, class, we're going to get started. You picked maybe the best, at least top 2 semesters to take How Things Work, or to take a physics class. I hope everyone heard, I don't know if you had a chance to catch up with the news, but I hope everyone heard yesterday was literally, I'm not exaggerating, one of the largest, most important announcements in physics in our lifetime. And that's not an exaggeration. So this was not the plan, but I have to at least spend a couple minutes talking about the announcement that was made yesterday. And so if you heard about it, you might be curious to learn more about it. If you haven't heard, then right now you're wondering what the heck just upended the world of physics. But so I do need to talk about that. So a good way to start is the first day of class, I brought up these 2 papers. And the first paper, 1686, that's Newton. Newton coming along saying, hey guys, this big, complex, amazing universe that we find ourselves situated in, I think I'm starting to get some of the laws that describe it. And we're starting to understand it a little bit. It's scary, I think, to be a human just wandering about a universe and not knowing if the sun's going to come up tomorrow, what governs, I don't know, light and cold and seasons in the sun. And so I think we humans have been, since there have been humans, have been trying to answer some of these questions about how the world works. And as I said the first day of class, I think we've been making some pretty good progress. We can trace that progress back thousands of years, but especially the last 300 or so years, we've been making some real progress. So we now know what elements are. That was a big one. We now know we're made of carbon and hydrogen and oxygen. We know what air is. We know what planets are. And as I've said in the last few classes, there's still about, roughly 95% that we don't know, but we're making some good progress. That second paper was published in 2012, and that second paper was CERN, was 2 collaborations at CERN, Atlas, and CMS, saying it's been about 300 years since Newton even gave us the concept of inertia. We think we might have figured out what inertia is, or where it actually comes from at the fundamental level. And so July 4th, 2012, there was this big announcement at CERN where Dr. Peter Higgs was there, and they said, we have found the Higgs boson. And that was a big deal. And at the time, scientists and non-scientists were paying attention, because really what that announcement was saying is that we have a new understanding about the universe. And whether you're a scientist or not, that should make you pay attention, that we have a new understanding about the universe. And so I'll repeat this for the next announcement, but if you're a physics major or an English major or a theater major, no matter what you are, if you're a human, you should be interested in science's progress in telling us what the world is about. And I think as humans, we should be interested in that. And so when we discovered that when Copernicus unseated the Earth from the center of everything, that changed who we were. That changed how we saw ourselves. And so science, if you're not a science major, that's still important. Science gives us new perspectives and new ways of knowing where we came from, what our ultimate fate is, how we should relate to one another. These are important things, I think, for any human to think about. And so 2012, we discovered the Higgs boson. Big deal, front page of the papers. We now really I think we pretty much get what mass is, and that was a big deal. And by the way, one of the things I should mention about the Higgs boson before I mention yesterday's announcement is that here's how the Higgs boson was discovered. There's one author on that paper on the left, Isaac Newton. Isaac Newton sat down, thought really hard, wrote out a paper, changed the world. Science nowadays is thousands and thousands of people. And so this paper right here comes from the Atlas experiment at CERN. 5,000 people at least are involved with that discovery. And so in fact, I was going to show, I'll pull it up in a minute. I have the paper I'll show in a minute, the last 10 pages are just authors. Because the way science is done nowadays, it's not one guy sitting in his basement thinking really hard. It's teams and teams it's an international collaboration with thousands of scientists and engineers working really hard, theorists and experimentalists and engineers, all working to get this one bit of data. And at CERN, the engineering side is at least as impressive as the physics side. Here's how we found a Higgs boson. We dug a tunnel underneath the Franco-Swiss border, 17 miles in circumference. So a tunnel, 17. So we were driving through this tunnel. It would take you 17 minutes to get through it. 17 miles around. We make that tunnel the coldest place in the universe and the best vacuum in the universe. If you were to go out to the far reaches of interstellar space, it would be warmer and less of a vacuum than the tunnel at CERN. And then we take protons, we accelerate them to 99.99999% the speed of light. That's 186,000 miles a second. These protons are going around. And then we bring them into a collision. And to bring protons, which are mutually repulsive, by the way, into collision, the analogy that's often used, it's like firing two knitting needles from either side of the Atlantic and trying to get them to hit head on. It's a quite impressive accomplishment. But then you're only halfway done. Then you have to take pictures and collect data out of that stuff moving near the speed of light. And you have to get that data to very high precision so you can draw conclusions that are valid. That's a pretty huge, it's a pretty huge theoretical leap to be able to conceive of that. It's a huge accomplishment, I think, as for us humans to sink the money into there, because the answer, if you were to ever ask a CERN scientist, what do you expect to get out of this? They just would say, more knowledge. We're not going to cure cancer with this. We're not going to, I don't know what else you would want to do with, make faster toasters or something. We're just going to expand humans' knowledge of the universe. That's our goal. So anyway, CERN has been doing that for decades, and they did it, and it was a massive, massive accomplishment. Okay, yesterday, here's two more papers. On the left, there's a paper written by Einstein in 1916. Einstein is one of those guys that sitting by himself, thinking really hard, changed the world, and maybe that'll happen again, but I think more and more it's these large collaborations. But so Einstein was sitting by himself, thinking really hard as a patent clerk at the Swiss Patent Office, and decided, oh yeah, maybe light is the same speed, maybe it's a constant in the universe, and he comes up with his special relativity in 1905, changes the world. Wasn't done then. Came along 10 years later, published his paper on general relativity, and gave us this idea, and this is crazy, but this is what Einstein said in 1915. He said that space itself, so imagine, again, the farthest, most remote regions of interstellar space, black nothingness. That space is a thing. It's a medium. It can be manipulated. It can be bent. It can be twisted. It can ripple. And so he says that space, and not even just space, space-time. And so he comes up with this concept of space-time. That space and time are two units of one continuum, and they're one thing, and that thing is a thing. Space is a thing. Space-time is a thing. It's just mind-blowing idea. And here's what's I think impressive about some of Newton's thoughts and about Einstein's thoughts. These guys are coming up with these thoughts at a time when they knew there was no way to experimentally confirm these ideas. And so you read these papers by Einstein that he and like Fermi or somebody are sending papers back and forth to each other, just thought experiments. I mean, they're just saying, okay, imagine you're riding on a beam of light, you've got a flashlight, and they're just coming up with these thought experiments knowing there's no way to actually ever experimentally confirm or refute any of what they're saying. Is that me? That is me. Okay. And so Einstein comes up with this idea of general relativity in 1950, and he says that space is a thing. It's called space-time, and it can be bent and manipulated, and it's general relativity. It's relative. So my time is different from your time, and your space is different from my space. Everything's relative. Crazy idea. And then he adds a little chapter in 1916, says, oh, by the way, if you play out the math, and not that we'll ever have to see this, but hey, I like playing with the math. If you play out the math, space can make, you can make gravity waves. Space can wave, and those are called gravity waves. So any mass, actually, so this is what he says in 1915 with general relativity. He says, any mass bends space-time. So you, right now, are making a little dent in space-time. So you may have seen like the mattress or rubber sheet example. So you can imagine the universe as a huge mattress or a huge stretched out rubber sheet. And you put a mass anywhere in that universe and it bends space-time. And so you are making a little divot, little distortion in space-time, you being massive. Well, planets make big dents in space-time. And suns and stars make even bigger dents in space-time. So that's what Einstein postulated in 1915. He says every mass makes these dents and distortions and twists in space-time. And in 1916, he says, oh, and here's one implication of that. If you move that mass around or accelerate it, it'll actually make waves. And we can call those gravity waves, because that dent can be thought of as really a representation of, or that is what gravity is. That's kind of what he's saying. That what you and I experience as gravity is really just warps and curves in space-time itself. And if you were to move a mass around, accelerate it, you would actually make waves of gravity. So that paper is 1916. Well, about 100 years, well, yeah, so 100 years later, they found them. They actually observed gravitational waves. That was yesterday. And I want to just tell you briefly how they did it, because it's nuts. It's nuts. So here's what they did. 1916, Einstein says, hey, we can make these things called gravity waves. Decades of scientists going, yeah, that's insane. And by the way, if we ever were, I mean, even if they do exist, we will never be able to detect them. We would need a detector so sensitive, probably not even physically possible. Only in the last couple decades have scientists started thinking, we might be able to pull this off. We might have the technology to do it. So we're just lucky to live in 2016 where we have the technology available that they have at the LIGO detector. And so here's about a decade or so ago, here's what some scientists proposed. They said, why don't we do this? Why don't we make a tunnel again? They're all about the tunnels. Why don't we make a tunnel 4 kilometers long, so about 2.5 miles long. And why don't we make another orthogonal tunnel, so another one at right angles, also 2.5 miles long. We'll make this big L-shaped lab. And so they built this big L-shaped lab, and they said, well, we might, just to be sure we're doing it right, let's build another one so we get confirmation data. So they built one in Washington State, and they built another one in Louisiana, and they built these 2 L-shaped labs. Each leg of the L is 2.5 miles long. And let's take a really, 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 really powerful laser and shoot it down the hallway, down that long tunnel, bounce it off a mirror, and have it bounce about 75 times back and forth before re-emerging out of the tunnel. And let's do that the same with the other leg, 75 times. And those 2 lasers should come back, and if the 2 legs of the tunnel are exactly the same, and we're talking exactly the same, those 2 lasers will actually come together and cancel each other out, and the little detector over here won't see anything, because the 2 lasers have canceled each other out. Lasers can do that. Waves of light can cancel each other out. Okay, so that's the idea. The idea is let's shoot lasers, like really powerful lasers, back and forth in these tunnels and just wait. And we'll probably never detect anything. It'll be, I think the initial investment was like $300 million, and it's about $30 million a year just to operate the thing. And let's just have, and they have to be kind of out in the desert to be away from, I mean, you're trying to detect these amazingly small signals, so, a car driving by screws everything up. So let's just haul all this stuff out in the desert, build these tunnels, 2.5 miles long, get the lasers going, and see what happens. And so they did that. They convinced the governments to, actually this was the NSF, so good job NSF. They invested the money, the National Science Foundation, and here's the most probable outcome, nothing. Best possible outcome, we see them, and there's no benefit for humans other than expanding our knowledge of the universe. So let's invest millions and millions and millions of dollars just because that's what humans do that. It's weird. Even no matter what the economy's doing, we're still trying to still put a man on Mars or something like that, which I love that about us. I think we should keep doing that. But so NSF invests all this money, and they just sit there, and they hear nothing for a while, which is the most probable outcome. And so they say, back, it was like about a year ago, they said, all right, let's see if we can make these things a little more precise. So they shut them down, and they go through a little phase of upgrading them, make the mirrors on either side better, make the detector a little better. And then last September, they flipped the switch on, and it was like a couple days later, their mirrors get a little wobble. And they went, oh my gosh. And they had already mathematical models of what a gravitational wave from space would look like. And I was reading an article yesterday where there was they had a picture of the grad student. He just looked like this, just looking at the screen. There was like a guy, I forget his name, but there was just a guy they're already giving him credit as not, he's not going to get the Nobel Prize, he's just some grad student, but he was the guy that first went. And it's amazing. So this guy saw this telltale little waveform, got on the phone. So he was in Washington, got on the phone, called the one in Louisiana, and asked them, did you guys see that? And they said, yep. And our two signals were about 7 milliseconds apart, which is exactly the expected delay of a gravity wave going through the Earth. So here's what they found. What they found is that, so just all of literally the planets aligning to make this happen is, so yeah, there's so much that's exciting about this now. So here's what happened. 1.3 billion years ago, two black holes were orbiting each other. So just, I could stop there, that's already amazing. So 1.3 billion years ago, two black holes are orbiting each other. And what was happening, both these black holes each had a mass of about 30 times the mass of our sun. So very large objects are orbiting each other very, very fast. And what's cool about black holes is they're so dense, they can get really close to one another. So if you took an object took two objects each 30 times the mass of our sun, you could never get them very close to each other because they're so big. But that same mass was packed down into basically zero space, so they got closer and closer and closer and closer. Eventually, they were orbiting each other at about half the speed of light. So these two things, 30 times the speed of the sun. So imagine, something 30 times the mass of our sun going 90,000 miles a second, orbiting another one going 90,000 miles a second. That was actually happening 1.3 billion years ago. And they started to bleed off some of their energy, and this does actually tie into our conversation that eventually I'll get back to about energy. We have a midterm and all that, so we should talk about energy. But there's energy. There's kinetic energy in that. So there's kinetic energy in this little dance that they're doing. That kinetic energy, and I've said I've tried to, I swear, like the last couple of days I've said multiple times, you can't destroy energy, you can't create or destroy energy. So the energy is actually leaving the system. And I don't know if I mentioned this because I didn't think it was going to be relevant to our conversations. You can take energy and put it into gravitational waves. That was not a relevant part of this class till about 24 hours ago, but there it is. So energy can be acoustic and thermal and all these other things. I should add to our list gravitational waves. So a lot, by the way, went into gravitational waves. Oh, actually, this is one of my favorite parts of the story is that so they spun down, and so they were losing some of their energy into gravitational waves. So they're sending out gravitational waves into the universe. And take two things going half the speed of light that are that big, going like this. They're orbiting each other at about 30 or 40 times a second, which is cool because that is if you plot the waveform and feed it through some speakers, it's audible. So the range of human hearing is about 20 to 20,000 hertz, 20 to 20,000 cycles per second. These things are going around about 30 times a second. So if you were to put that waveform at the gravity waves, you were to put that into a speaker, you would just hear boo. That's 30 times a second. But then as they lose energy as gravity waves, they got closer and they sped up, and they got closer and sped up and closer and sped up, and they spiraled into each other, and they formed one black hole. So these two black holes spun faster and faster until they were going about 300 times per second, which is, I think middle C is 3 something, and I don't know if anyone knows. I'm not a musician. But, I actually saw another video. That's all I've done in like the last 24 hours. But somebody took their finger on the 20 hertz end of the piano. It's like the lowest one. And if you just run your finger up to middle C, that's pretty much the sound that these black holes made. They went, boop, and they went up, and then they stopped because that was it. They were now one black hole. There's nothing orbiting anymore. So they spun into each other, and they merged into one black hole. And in doing so, right at the end there, they emitted 3 solar masses worth of energy as gravitational waves. So it was roughly a 30 and a 30. The paper's right there. 36 and a 29. So 36 and 29 solar masses of stuff, 3 solar masses of energy, so 3 times the energy of our sun, got sent out as gravitational waves. In that instant where they merged, the power, again, this is back to our conversation about energy, power is the rate of energy. The power of that moment was greater than all of the stars in the universe combined. The rate of energy dissipation in that moment was greater than the rest of the universe. It's a big event. So that was 1.3 billion years ago. 1.3 billion years ago, that happens, and these waves go out into space. And they travel through space, and they travel through space, and they travel through space. We happen to be conveniently far enough away, because if we were right there, we would have, we would have been destroyed, but also there wouldn't have been humans yet, and we wouldn't have built detectors yet. So fortunately, we were just far enough away that it took, what was going on 1.3 billion years ago? There was a planet, I think there was life, I don't think there were humans yet. So while these waves are traveling through space, humans show up, humans evolve, we develop civilizations, we have wars, there's civilizations rise and fall. The whole time, gravity waves are on their way. And so it's almost a race. We don't even know. It's a race. Can we build our detector by the time they get here? And so then we make a country, and we make currency, and we make scientists, and they make scientists, and they get their PhDs, and they teach other people, and the whole time the gravity waves are just on the way here. And then they're almost here, and somebody goes, why don't we build a detector? And they build this detector. It's not going to, and it doesn't get anything, and then they do an upgrade, they flip it on, right as these gravity waves that have been traveling at the speed of light for 1.3 billion years, right as those waves wash past our planet and keep going. And so there was this about fifth of a second in all of human history where that wave that was been traveling here for 1.3 billion years, for about a fifth of a second, those waves were detectable, and we happened to have two detectors sitting on two sides of the United States that went whoop, and that was it. And so our detectors that we spent decades designing and building, all that went whoop did that in September, and they released the paper yesterday. And so what's great is that these two detectors, they both got the same signal. The signal was absolutely characteristic of two black holes. I forget there's a term for spinning into one. Two black holes spinning into one. It was exactly the signal they expected, and they were matched. The two experiments got the same signal, but just the right time apart to show that it was a black hole moving at the speed of light, or it was a gravitational wave moving at the speed of light. So, oh, by the way, I forgot. I have all these nice pictures. There's Ligo. That's one of them. I think that's the one in Washington. So Ligo, the Laser Interferometer Gravity Wave Observatory. Oh yeah. So I should also mention. I should also mention a little bit more about how sensitive these things are. So here's the crazy thing. So they built these two long L-shaped tunnels, and the laser goes back and forth. So when a gravity wave passes through you or through where you are, it's a ripple in space itself. So if a gravity wave were to go through this room this way, we'd all get, it would be a wave. So we would all get shorter and fatter, shorter and fatter, shorter and fatter as it went, or like skinnier, fatter as it went through. Or if it went this way, we'd all get shorter, taller, shorter, taller, shorter, taller as it went through. So it's actually a wave in space itself. So the reason we have this laser bouncing back and forth is we can detect that and that's why we have two of them, if a wave goes this way or goes this way, it'll affect the two arms differently. And so if we detect that one of the arms got shorter, that was a gravity wave. And here's the amazing science, or here's the amazing engineering really behind it all. Or it was somebody sneezing, or a truck going by, or any other millions of things. So the fact that they can even filter out all the noise is incredible. The mirrors are actually hung they're hung like pendulums from the ceiling, and there's all these measures to make sure it is like perfectly still. So the leg gets a little bit shorter. And here's, again, just, humans, this is nuts. It got shorter. It got shorter by about 1/10,000th the diameter of a proton. So when that gravity wave went through, you kind of, what you visualize is the thing getting shorter, which it actually did get shorter, but by an amount comparable to if the distance between here and Pluto changed by 1 human hair width, we detected that. So the distance between here and Pluto shrunk and then grew by the width of a human hair. That's how sensitive this. I'm not making this up. It's in the paper. I swear. How do you do that? It's just amazing engineering and science in order to do that. But that's what we detected. So there's a picture of LIGO. And again, here's there's a lot of reasons to be jumping up and down, but maybe this is the last one I'll mention before we got to talk about some energy and stuff. Like I said, it doesn't matter if you're a science major or not. This is literally yesterday they opened up a new realm of astronomy and cosmology. And here's why. Up till yesterday, if I I wanted to see anything outside of about a meter away, I had to look at it with light. So I want to know what's in this room. I could walk around and touch it, or I could look at it. Those are pretty much my options. Same goes for astronomy. I want to know what's on the moon. I can look at it or go there. So we've done both. We've looked at the moon. We've gone there. But we can't go that far. Like, the universe is just too big. So we're left looking at stuff. That's kind of how we know what we know about the cosmos, is we've looked at stuff. We put our telescopes up and we look, and we make bigger and better telescopes that can look really good, but we're still just looking with light. That's all we've ever done since Galileo. We've relied on light to tell us about the universe. Now we have better telescopes now called radio telescopes that look at light outside of the visible spectrum, but it's still light, it's still photons, still electromagnetic radiation. And so all of the telescopes ever built in the history of mankind have relied on this one thing, the light, or technically a photon. And like I said, you could be infrared light or ultraviolet light. It could be invisible to humans, but it's still light. As of yesterday, we have a new ear on the universe. We have another way of looking at the universe. It's like all of a sudden someone turned the lights on. If you spent your whole day trying to figure out who's in this room and where's the computer and where's the desk with your eyes closed, and all of a sudden the lights are on, you have another mode of exploration, another mode of knowing, which I don't think I'm over emphasizing. That's super exciting. I think just for anybody, whether you're an astrophysicist or not, it's a big day. So stay tuned. Maybe some more data and stuff will come out from the Ligo experiment. But go Ligo. I'm sure Nobel Prizes will be on their way to those guys. Okay, so there's the Ligo experiment. Here's 2 artist renditions of what orbiting black holes would look like. One sort of interstellar looking, and so they're on their way to merging, and then there's a picture of what 2 black holes might look like. And there's that picture is, that's the waveform. And so you can see the top is the actual waveform, and the bottom is zoomed in just to that last very short amount of time. So yeah, you can actually hear it. It goes through the audible range. It's like whoop, and it's this little chirp that goes up to like 250 or 300 hertz, which is, yeah, you could listen to it. So it's a nice little noise. Okay. And then last one. This morning I was reading the Atlantic. It says a dawn of a new era of science. I don't think that's an exaggeration. Cosmic breakthrough. That was the post this morning. So, and there's the guy making the announcement from LIGO, and it was funded by the NSF. Go us. Okay. That leaves me with 16 minutes to talk about energy. Actually, you know what that does? That gives me 16 minutes to take advantage of all these toys up here. So let's talk about energy and energy transfer, and go through some of the demos that I have up here. So I'll forget if I don't do it now. Let's do an eye clicker. Then we'll talk about some energy transfer. Yeah. Oh, I gotta start it. Oh, by the way, I finally tried to give you an eye clicker question. It's actually relevant to like your homework or the midterm. So this is a good midterm question. And not that we've talked about many of these units before, but I do want to get us thinking about the units of energy, especially versus the units of power. Yep. Pardon? Oh, British thermal units. If you've ever bought a water heater, they're usually listed in BTUs. Good, you guys got my hint. All right. I love watching the exodus out of column A. Okay. There we go. Good. Take about 10 more seconds. Make sure you're buzzed in on E. Some holdouts for BTU. All right. That's fine. That's fine. All right. There's only 187 of us here today. That means 53 of us are home reading about gravity waves. That's fine. And that looks like we're stuck at 187. Okay. Just real quick, that is a good midterm review question. We're talking about work, energy, and power, I guess would be the summary of what we're talking about right now. We're talking about energy. That's really what we're talking about. Energy is a great way to understand the universe. As I mentioned last class, I think, or 2 classes ago, there's just one universe, and it is governed by Newton's laws, but we've developed basically 3 really good frameworks for understanding it. And so we're not going to get to impulse and momentum before the midterm, but we will have talked about 2 frameworks for understanding the universe. I want to understand why the universe does what it does. I can understand it using Newton's laws. That's a great tool for understanding the universe. But there's another one that sometimes is more efficient. It's not a different universe. It's just sometimes using the concept of energy, work and energy, is a better way to understand the universe. And so that's what we're talking about right now. So energy. And so then I need to know, and so the concept is that energy cannot be created or destroyed. It just changes form. Sometimes it changes into the form of a gravity wave. Sometimes it changes from potential into kinetic. Sometimes it changes from kinetic into thermal. But it can't be created or destroyed, but it just changes forms. And that understanding sometimes is the best way to understand what's going on. And so today, in the next 12 minutes, I'm going to try to give you some demonstrations of that happening, of energy changing forms. So I'll put that slide back up in a minute. We measure energy in joules. We measure the rate of usage or change of energy in watts. So if you've ever looked at a 100-watt light bulb, right here is a 15-watt light bulb. If you've ever read the wattage number on a light bulb, what that is telling you is how many joules per second that light bulb's going to use. So wattage is joules per second. Or more generally, power is energy per time. And so when you get your bill from the power company, it's usually in like kilowatt hours. What that is, that's a weird term, because it's thousands of joules per second times hours, but it gets you back to energy. By taking wattage, which is power, and multiplying by time, it gets you back to energy. So wattage is, or power is energy per time. Multiply that by time, like hours or something, you get back to energy. So when you get when your power company says blah 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 kilowatt hours, that's a measure of how much energy you use, not a measure of power. Calorie is just another type of energy. So I think we all know you need calories to get energy. So you eat your breakfast, you have energy to do work. BTU is just another type of energy that, like I said, yeah, if you ever buy a water heater, or I think that's the only time I've seen it, you go to Lowe's, the yellow sticker, sometimes it's a lot of those power ratings are rated in BTUs, British thermal units, which is similar to a joule. A joule is the amount of energy to raise a cubic centimeter of water 1 degree Celsius. A BTU is the amount of energy to raise a gallon of water 1 degree Fahrenheit. But that's a crazy type of unit. Just about as crazy as horsepower. But so horsepower is a measure of power, and it's a measure of how quickly you can do energy. So I'm not as strong as a horse, but I actually can produce 1 horsepower, because horsepower is just the rate at which a horse, like the average horse, can put out energy. And I think the average horse can put out 750 or so watts. So next time you're at the gym, find one of the bikes that'll measure wattage. See if you can get up to 750. That's like Lance Armstrong style energy, but I think you could probably get up to 750. Give it a try. Okay. Lance Armstrong on performance-enhancing drugs. All right, that's enough iClicker. I want to get through some of these demonstrations. So what I'm about to show you is just like 5 different versions of the whole story, the whole important story, and that story is transfer of energy, doing work. So I'll start with the light bulb. I have a light bulb here that's not on. Oh wait, I think I might be able to change my camera. Let's go to here. There it is. Okay. Here's a light bulb that's not on. The reason it's not on is there's no energy going through it. If I were to see light and probably feel heat, that's energy. Light is energy, heat is energy. So if I want this thing to generate light and heat, I need to give it some energy so it'll do that. The way I give it energy is I actually burn some of my breakfast. So the whole story before, light goes down, hits the wheat, we harvest that, turn it into a bagel, I eat the bagel, and now I'm actually, hopefully we can see that, there it goes, it's on. So I'm actually taking mechanical energy, mechanical work, I'm doing mechanical work, and I'm actually expending energy. That energy is going into kinetic energy, which this little motor is converting into electric energy, and I'm lighting up the light bulb. And here's your quick energy conservation lesson for the day. That was an incandescent bulb. The way incandescent bulbs work, it's a bad idea. I'm glad we're finally getting past it. Just make something so hot it glows. That's how incandescent bulbs work. And it's if you ever see an incandescent bulb glowing whitish, like most of them try to do, that means, and I'm not making this up, it's about the temperature of the surface of the sun. That's how you make something white. Like we humans love that color because we've been living under it for millions of years. How do you get something that bright? You have to get it to the surface of the temperature of the sun. And the bad thing about that is most of the energy coming out of here is not visible. So it's mostly wasted. Here's a fluorescent bulb, better system. I can make that nice and bright. Same mechanical work. I'm going about the same speed. I think I'm getting a little more light energy out of that. But again, it's my breakfast going into light, much less of it into heat. Because this is fluorescing, not incandescing. So I'm actually just exciting gas molecules, which is way smarter than just heating something up to the temperature of the sun. Here's the smartest thing we've done in a while. We've forgotten about all that, and we've actually just convinced some silicon atoms to emit photons, to emit light. And that's just LEDs. That's so bright. That's just LEDs. I don't know if you've bought LEDs. If you haven't replaced all your bulbs yet with LED bulbs, they're amazing. This thing sips electricity. This thing's 15 watts. I bet this is a quarter of a watt, if that. They just, it takes almost, because all the energy is being almost entirely transmitted into light. So here's my breakfast. This is my breakfast as light. It's almost entirely going into light, as opposed to wasted heat and invisible forms of light. Bad idea. That one's awesome. Okay. 6 minutes left. Let's do this guy. I like let's see how do you see that? That is, you have to see let's do side projector document. That guy. There it is. Okay. Pretty similar idea. I'm going to take mechanical work and I'm going to put my energy, again, my breakfast. I'm going to put mechanical work and I'm going to press down. When I push on this lever over here, which is off the camera, you can't see it. When I push on this lever, I'm actually squeezing a piezoelectric crystal. If you've never heard of a piezoelectric crystal, if you've ever lit a grill or anything and heard that click, that click you're hearing is a little spring-loaded hammer hitting a crystal. And let's see, if you've ever had a quartz watch, I don't know if those still exist, but a quartz watch is doing the same thing. It's pinging a little crystal. And there's certain crystals that if you squeeze them, they actually create electricity. Piezoelectric, squeeze electric. So there's a piezoelectric lighter in here. So I don't know if you've ever accidentally touched the tip of one of these when you're hitting it. It gives you a little electric jolt. Because that little click, the hammer, you're hitting a hammer hit a crystal, and that's generating electricity. So I've got one of those crystals right here, and when I push, can you guys see that little spark? There it is. So when I push my hand on this lever, it squeezes a crystal, and that crystal generates electric potential, and we can see it in the spark up on the screen. So that spark is, again, this is the whole point of these demonstrations. breakfast, mechanical work, going into pressure, which is kind of elastic energy, then that's being released as electric energy, and ultimately as light and sound. You're hearing tiny baby thunder. I don't know if you can hear it. Hear that? That's tiny baby thunder you're hearing. And I just realized I could do this. Okay. And so ultimately my breakfast is going into light. You're seeing the spark, and you're actually hearing the expanding air from when I'm ionizing the air due to all that voltage. I'm creating voltage, which is nice. Okay. Oh, we got to do this one. Okay, again, whoops. I don't want you to hear, that's not what I was hoping you'd listen to. Can you hear the click? Again, there's a piezoelectric device in here. So there's a spring. There's a spring that gets loaded, and it clicks, and it hits a piezoelectric little crystal. That crystal shoots a low electric current that lights the gas. And all of this just for like a pretty simple demonstration, but it's fun to do, so we're going to do it. We're about to watch gravitational potential energy do work. So that's what that is down there. So I got to, let's see. Got to be on camera. Is that on camera? Oh, wait. I broke it. Oh, no. Side project. Okay, well, I don't know if it's going to be on camera. Shoot. Let's go center projector, left camera. Okay, there it is. So this is a pretty simple demonstration, but fun to do. We're going to watch gravitational potential energy go into work. And again, the definition of energy is the ability to work. Work is the transfer of energy. And so I want to do work. What work do I want to do? I want to drive a nail into that piece of wood. I need energy to do that. Here's how I'm going to get the energy. I'm going to get the energy from the gravitational potential energy of that weight. That weight is 10 kilograms. It's like, I don't know, let's call that half a meter. So that's about 500 joules of energy I've got right there. Let's see if I can, and I'm going to release it with an unnecessarily impressive amount of energy coming out of here, so why not? All right. So I just drove that nail straight through a piece of wood using gravitational potential energy. That's a fun demo. Totally unnecessary, but awesome. I got one more. I have one more. And here is the power company. I think, like I said, I think we're a customer of Dominion Power. Power company is using nuclear energy to heat water, to create electricity, sending over here. That electricity is coming through here, which is going to generate light. I've got a solar panel on there, and using that solar panel, I can convert this light energy into mechanical energy, and I can make a little car drive across the floor. So that's exciting. That's a solar car. Let's call it a day. Okay, thanks. Wow, all right.